Tonight, the journey begins far beyond Earth in the quiet darkness of space, where distant stars, silent planets, and endless galaxies drift in calm motion. This is a place of wonder, scale, and stillness. For the next 10 hours, gentle space facts will unfold slowly, creating a peaceful path into rest. Before settling in, please like the video, subscribe to the channel, and let the calm of the universe carry the night gently forward. Across the observable universe, matter and light fill a volume so large that it is described not by edges but by horizons. The horizon is set by time and by the finite speed of light. Light travels through space at a fixed speed, and the universe has a finite age. So there is a limit to how far any signal can have travelled since the earliest times. Everything that can be observed lies within that limit. Beyond it, there may be more space and more galaxies, but they remain outside present observation. The universe is not static. Measurements of distant galaxies show that, on average, they move away from one another, and the farther they are, the faster that recession appears. This pattern is understood as the expansion of space itself. Expansion does not mean that galaxies fly through a central emptiness. It means that the distances between large, gravitationally unbound structures increase over time as the fabric of space stretches. On smaller scales, gravity holds systems together. Within a galaxy, stars remain bound. Within groups of galaxies, the closest members can remain tied by gravity. The expansion becomes dominant only across the great voids that separate clusters. The present universe carries the imprint of its early conditions in a faint glow that reaches Earth from all directions. This glow is the cosmic microwave background, radiation left over from a time when the universe cools enough for light to travel freely through space. Today it is seen as microwave radiation because the expansion of space stretches its wavelengths. The cosmic microwave background appears nearly uniform, but careful measurements reveal slight variations in temperature. Those small differences correspond to tiny differences in density in the early universe. Over billions of years, gravity amplifies those differences, drawing matter into filaments and nodes. The result is a large-scale structure that resembles a web, with galaxies and clusters tracing long strands around enormous emptier regions. Matter in the universe is not all visible. Multiple lines of evidence indicate that most matter is dark matter, a form of matter that does not emit or absorb light in the usual way, yet reveals itself through gravity. Galaxies rotate in ways that require more mass than can be seen. Clusters of galaxies bend and distort the light of more distant objects by gravitational lensing, and the strength of that lensing implies large reservoirs of unseen mass. Patterns in the cosmic microwave background also indicate a dominant component of non-luminous matter. Dark matter gathers first, forming halos that act as gravitational scaffolds. Ordinary matter, made of atoms, falls into those halos, cools, and forms stars and galaxies. Alongside matter, there is another component that shapes the universe on the larger scales. Observations of distant exploding stars called Type I supernovae show that the expansion is accelerating. This implies a form of energy associated with space itself, often called dark energy. Dark energy is not understood in detail, but its effects are measured through the expansion history of the universe and through the distribution of galaxies. As the universe grows older, this accelerating expansion makes the most distant galaxies recede ever more quickly, over very long times. This trend means that many galaxies will slip beyond the observable horizon, not because they vanish, but because their light will no longer reach an observer. The age of the universe is inferred from several independent measurements, including the cosmic microwave background and the current expansion rate. These methods converge on a value near 13.8 billion years. That span is long enough for several generations of stars to form and die. The earlier stars formed from gas composed almost entirely of hydrogen and helium, the simplest elements produced in the first minutes after the Big Bang. In the cores of stars, nuclear fusion builds heavier elements, and the most massive stars end in supernova explosions that scatter those elements into space. Over time, later generations of stars form from enriched gas that contains carbon, oxygen, silicon, iron, and many other elements. These elements are essential for rocky planets and for the complex chemistry associated with life on Earth. Across this vast age and volume, galaxies become the primary islands of concentrated matter. A typical large galaxy contains vast numbers of stars, along with gas, dust, and dark matter. Galaxies evolve over cosmic time through steady star formation, through the slow inflow and outflow of gas, and through gravitational encounters with neighbors. Some collisions lead to mergers that reshape galactic structure. In many galaxies, a central black hole influences its surroundings when gas falls inward and releases energy. Distance in the universe is not only large, it is layered with time. Light from a nearby star reaches Earth after years. Light from a nearby galaxy reaches Earth after millions of years. Light from the most distant galaxies reaches Earth after billions of years, carrying information from an earlier universe. Astronomical observation therefore reveals change across time as well as space. It shows that galaxies grow and transform, that star formation rises and falls, and that the chemical richness of the cosmos increases as generations of stars live and end. On the larger scales, travel is shaped by two firm constraints: the immensity of distance and the speed limit set by light. Even without considering engineering or biology, those constraints impose long durations on any passage between far-separated systems. Cosmic expansion adds a gentle but persistent widening between unbound regions, so that the gaps between galaxies are not fixed. Over the long term, the accelerating expansion driven by dark energy increases that separation further for the most distant galaxies. The observable universe therefore appears as a calm, structured expanse governed by measurable principles. It has a finite age, and it expands. It contains dark matter that shapes the growth of structure, and dark energy that accelerates expansion. It contains galaxies that assemble and enrich their surroundings with the elements needed for complex worlds. Within and between these galaxies, space remains mostly empty. Yet it is not nothing. It carries thin gas, faint radiation, and the long memory of early conditions preserved in background light. Across this expanse, potential locations for life may be numerous in count, but widely separated in space and in time. Between one galaxy and the next, space opens into distances so large that ordinary intuition loses its grip. A galaxy is already immense, with stars spread across tens of thousands of light years or more, yet the gaps between galaxies are often larger still, extending across hundreds of thousands or millions of light years. These separations define the broad geography of the universe beyond any single galactic home. In this region, galaxies do not form a continuous field. They gather in groups, clusters, and long filaments, with wide voids between them. The pattern is sparse, structured, and quiet. A galaxy appears from far away as a concentrated island of stars, gas, dust, and dark matter. Some are graceful spirals with broad arms and flattened disks. Others are elliptical systems, rounder and smoother in appearance, with older stellar populations and less cold gas. Still others are irregular, shaped by interactions or by smaller mass. Their visible forms differ, but each remains only one node within a much wider network. The network stretches across millions of light years, and even its denser parts are mostly empty space. These large separations matter because any discussion of movement between civilizations begins with geography. If life arises in many galaxies, the first obstacle is not the number of potential homes, it is the gulf between them. A signal sent across intergalactic space must travel for millions of years to reach even the nearest major galaxy beyond the local neighborhood. A physical craft, moving far slower than light as all known matter must, would require far longer. The issue is not only engineering, it is time itself. Any journey on that scale must persist through spans much longer than recorded human history, longer than the rise and fall of species on Earth, and often longer than the stable lives of many stars. The nearest large galaxy to the Milky Way is Andromeda, at a distance of about 2.5 million light-years. This makes it close in cosmic terms, yet still extraordinarily remote. Light leaving Andromeda reaches Earth after travelling for 2.5 million years. It begins its journey long before the appearance of modern humans. Any material object would take at least that long if it could somehow travel at the speed of light, which known physics does not allow for objects with mass. At slower but still extreme speeds, the journey lengthens dramatically. At 1/10 of the speed of light, it would take roughly 25 million years. At lower speeds, it would stretch into spans that are difficult even to picture as a continuous project. The intergalactic medium, the thin material between galaxies, is not entirely empty. It contains very diffuse gas, mostly hydrogen and helium, along with traces of heavier elements spread by galactic winds and ancient explosions. It also contains radiation fields and magnetic structures on large scales. But none of this fills space densely enough to make the medium erode. It remains a vast, cold, tenuous expanse. A craft crossing it would find little to interact with and little to use. There would be no close stars for easy support, no dense clouds for regular refueling in any familiar sense, and no stable chain of nearby worlds. The journey would pass through darkness broken only by distant galaxies and isolated foreground stars within the traveller's own departure galaxy for the early part of the route. Galaxies also move relative to one another, but these motions rarely simplify the problem. Within bound groups and clusters, gravity can pull galaxies together. The Milky Way and Andromeda, for example, move toward each other and are expected to merge far in the future. In larger terms, however, galaxies outside local gravitational bonds generally recede as the universe expands. This means that many potential destinations are not merely far away, they are becoming farther away over time. For the most distant galaxies, this recession grows so strong that light emitted now may never arrive at certain future observers elsewhere. Expansion, therefore, turns the largest cosmic scale into an environment where separation is not fixed but increasing. Clusters of galaxies show how matter gathers on large scales. A cluster may contain hundreds or even thousands of galaxies bound together by gravity. Within a cluster, galaxies orbit through a shared halo of dark matter, and hot gas fills the space between them, glowing in X-rays. These regions are denser than the cosmic average. Yet even here the individual galaxies remain widely spaced compared with their own sizes. direct collisions between stars are still extraordinarily rare even when galaxies interact, because stars occupy such a small fraction of the total volume. The cluster is a crowd only by cosmic standards. By ordinary physical density, it is still almost empty. This arrangement has an important consequence for the possibility of advanced civilization spreading far from home. If a civilization arises in one galaxy, reaching another galaxy is a very different task from moving between stars inside its own. Within a galaxy there may be long but manageable stepping stones in principle, with stars and planets distributed throughout the disk or halo. Between galaxies, the stepping stones largely vanish. The voyage becomes a passage across a deep interval with few local resources and with durations that could outlast the civilization that launched it, unless the mission is designed to survive profound stretches of time without continuity of culture or leadership. There is also the problem of detectability. A civilization in another galaxy may use energy on scales that are large by planetary standards, yet still be nearly invisible at such distance. Radio signals weaken with distance. Artificial light on planets is lost beneath the brightness of host stars. Even large engineering projects would be difficult to distinguish across millions of light years unless they altered the light of a whole stellar population or released unusual energy in a way that current astronomy could clearly separate from natural processes. Observations of other galaxies reveal stars forming, black holes feeding, and gas moving, but they do not reveal confirmed evidence of technology. This absence does not prove that no civilization exists beyond the Milky Way. It means only that no clear signal stands above the enormous distance and the many natural sources of light. For these reasons, intergalactic space sets a natural outer limit on practical contact. It is not an absolute impossibility in the sense of logical contradiction. Known physics does not forbid matter from crossing from one galaxy to another at sublight speeds. Galaxies themselves exchange material during interactions, and stars can be stripped into long streams. But for an intentional traveller, the burden is severe. The travel time is immense, the route is poor in resources, and the destination may itself shift over the course of the mission. The region between galaxies therefore serves as a filter. It does not remove the possibility of life elsewhere, but it makes rapid exchange between distant galactic civilizations deeply unlikely under known physical law. Any advanced beings already on their way from another galaxy would need to have begun their journey in a remote past and to sustain it across spans that surpass the history of human civilization by many orders of magnitude. In the broad cosmic setting, this pushes the more realistic search inward, away from the great gulfs between galaxies and toward the nearer structures where gravity gathers matter more closely together. The local group is a small archipelago of galaxies bound together by gravity within a wider ocean of expanding space. It is defined by shared motion and mutual pull rather than by any sharp boundary. Its members drift through a common volume a few million light-years across, their paths shaped by overlapping dark matter halos and by slow encounters that exchange gas and stars. The local group sits inside the larger cosmic web, yet it behaves as a gravitationally connected neighborhood. Two large spiral galaxies dominate this neighborhood. The Milky Way and Andromeda contain most of the local group's stars and most of its visible mass. Their gravity sets the overall rhythm of the group, and many smaller galaxies orbit one or the other. A third sizable spiral, the Triangulum Galaxy, is less massive but still substantial, and it participates in the group's dynamics. Around these larger systems, dozens of dwarf galaxies form a scattered population. Some are irregular, with clumps of young stars and remaining gas. Others are dwarf spheroidals, faint and gas-poor, with mostly old stellar populations. Their diversity reflects both their initial conditions and their long exposure to the gravitational environment of the group. The distances inside the local group are large by human standards, but small compared with the separations between major galaxies elsewhere. Andromeda lies roughly 2.5 million light-years from the Milky Way. Triangulum lies at a similar scale of distance, with remaining uncertainty, because distance measurement depends on calibration and method. These separations still mean that light takes millions of years to travel from one major galaxy to another, yet the group remains compact enough that its members are not carried apart by the overall expansion of the universe. Within this region, the mutual pull of gravity exceeds the gentle stretching of space that dominates at larger scales. Dark matter provides much of that binding. It is inferred because the visible mass of stars and gas cannot account for observed motions. The main galaxies sit within extended dark matter halos that reach far beyond their visible stellar distributions. Those halos influence the orbits of dwarf galaxies and shape the future paths of the largest members. The local group's combined dark matter forms a shared gravitational framework that keeps the neighborhood together. The dwarf galaxies of the local group are more than small companions. Many preserve long records of how galaxies grow. Low-mass systems have shallow gravitational wells, so they are sensitive to processes that strip gas, heat it, or prevent it from cooling. When a dwarf passes close to a massive galaxy, tidal forces can stretch it, pull stars into streams, and remove dark matter from its outskirts. Hot gas surrounding a large galaxy can also strip gas from a dwarf, reducing or ending star formation, and leaving a faint remnant dominated by older stars. Observations reveal disrupted satellites and stellar streams that trace these encounters as faint arcs across the outskirts of the larger galaxies. These structures show that the local group is active on slow timescales, with gradual accretion and rearrangement continuing today. Chemical enrichment across the local group follows those histories. Many dwarf galaxies contain lower fractions of elements heavier than helium than the larger spirals, because fewer generations of stars have formed or because enriched gas escapes more easily. Some dwarfs show evidence of early star formation followed by long quiet periods. Others continue forming stars at low rates where gas remains. These differences matter because rocky planets depend on heavier elements such as oxygen, silicon, magnesium, and iron. Though the presence of those elements alone does not determine whether life appears, the motions of the Milky Way and Andromeda offer a clear example of local group dynamics. Measurements show that Andromeda approaches the Milky Way with a significant component of velocity along the line of sight. The sideways component is smaller and more difficult to measure, but current evidence indicates a future merger several billion years from now. The process involves repeated passages and gradual settling as gravity reshapes orbits and funnels gas. Such mergers are common in galaxy evolution. They redistribute stars, thicken or erase disks, and can increase star formation if gas is available, while also heating and scattering stellar orbits. Within the local group, long intervals of relative calm exist alongside these slow interactions. A galaxy can orbit for billions of years without a disruptive encounter if its path remains distant from the main attractors. For the development of life, stability is one ingredient among many. The broader group environment influences how often galaxies interact, how gas is supplied or removed, and how stellar populations change over time. but the conditions on any particular planet depend more directly on its star and on the planet's own geology and atmosphere. For any advanced civilization that arises in this neighborhood, the local group sets the nearest intergalactic horizon. The distances between galaxies remain immense, yet they are the smallest intergalactic distances available. Communication by light or radio is possible in principle, but signals still require millions of years to cross between the main galaxies. Physical travel would demand endurance across those same spans unless speeds approach a significant fraction of the speed of light, which requires extreme energy and introduces serious challenges from radiation, dust impacts, and long-term reliability. These constraints do not remove the possibility of travel, but they place it firmly into the realm of deep time. The local group thus forms a bridge between the scale of the universe and the scale of a single galaxy. It gathers a limited number of nearby galaxies into one gravitational family, each with its own mixture of stars, gas, and dark matter, and its own record of growth through interaction. It is close enough for detailed study, allowing astronomers to resolve individual stars in many members and reconstruct their histories. It is also vast enough that movement between its main islands remains extraordinary. Within this quiet neighborhood, the potential for life elsewhere remains uncertain. The processes that form stars and planets operate throughout the local group, but observations so far confirm life only on Earth. What remains unknown is how often life begins, how often it becomes complex, and how often intelligence develops technology that endures long enough to matter on intergalactic scales. The Milky Way extends across the local group as a barred spiral galaxy, broad and layered, with most of its visible light concentrated in a flattened disk and a luminous central bulge. From within it, the full shape is not seen directly in one single view, yet its structure is reconstructed through maps of stars, gas, dust, and motion. It is a system of many hundreds of billions of stars, immersed in a much larger halo of dark matter that reaches far beyond the visible edge. The galaxy does not sit still. It turns, slowly and continuously, carrying stars and gas around its center over spans of hundreds of millions of years. The disk is the most prominent stellar region. It contains spiral arms, not as rigid structures, but as large-scale patterns where stars and gas are concentrated more strongly than in neighboring regions. These arms are rich in cold gas and dust, and they are active sites of star formation. Massive young stars light nearby clouds and trace the arms in blue and white light, though much of that light is dimmed or reddened by interstellar dust. The disk also contains older stars, open star clusters, and the raw material from which future stars and planets may form. It is both a settled environment and an active one, with quiet orbits unfolding beside regions of compression, turbulence, and collapse. At the center of the visible galaxy lies the bulge, a dense concentration of stars with a more rounded form. The Milky Way's bulge has a boxy, elongated shape linked to the bar, a central structure made of stars that stretches across the inner galaxy. This bar helps move gas inward through gravitational torques, which are turning effects that shift angular momentum and slowly rearrange material. The central regions are more crowded than the outer disk and contain older stellar populations on average, though they also include gas clouds and young stars in selected areas. Hidden at the dynamical center is a supermassive black hole, Sagittarius a star, whose mass is measured through the fast orbits of nearby stars. At present it is relatively quiet compared with the bright active nuclei seen in some other galaxies. Above and below the disk lies the stellar halo, a sparse, extended region containing old stars and globular clusters. Globular clusters are dense, gravitationally bound swarms of very old stars, often containing hundreds of thousands of members. They orbit in wide paths that are not confined to the galactic plane. The halo also contains streams of stars, remnants of smaller galaxies and clusters pulled apart by the Milky Way's gravity. These streams reveal that the Milky Way grows in part by accretion, the gradual capture and absorption of smaller systems. The process is slow, but its record remains visible in the motions and chemical compositions of stars. The interstellar medium fills the spaces between stars with gas, dust, magnetic fields, and high-energy particles. It is not uniform. Some regions are hot and very thin, heated by supernova explosions and stellar winds. Others are cooler and denser, forming clouds of atomic or molecular gas. Molecular clouds are especially important because they are cold enough and dense enough for gravity to gather material into star-forming cores. Within these clouds, dust grains shield the interior from harsh radiation, allowing molecules to survive and temperatures to remain low. Under the pull of gravity, parts of the cloud contract, fragment, and eventually ignite nuclear fusion in newborn stars. Dust, though only a small fraction of the interstellar medium by mass, shapes much of what is seen. It absorbs and scatters visible light, obscuring distant stars and making some parts of the galaxy difficult to observe at optical wavelengths. Yet the same dust glows in infrared light, allowing telescopes sensitive to longer wavelengths to map hidden structures and cold star-forming regions. Dust grains also carry chemical importance. Their surfaces help simple atoms combine into molecules, including molecular hydrogen, which is common in the coldest clouds. These grains later become part of protoplanetary disks around young stars, contributing to the solid material from which rocky bodies can form. The Milky Way is chemically mixed but not uniform. Stars near the galactic center tend to contain, on average, a higher abundance of elements heavier than helium than stars in the far outer disk or in many halo populations. This pattern reflects the history of star formation. Regions that have formed many generations of stars become progressively enriched as stellar winds and supernovae return heavy elements to interstellar space. Those elements are then incorporated into later generations of stars and into the planets around them. This enrichment matters for solid worlds because rock and metal depend on elements forged inside earlier stars. Motion inside the galaxy follows gravity but remains complex. Stars in the disk orbit the center in roughly circular paths, though not all at the same speed in the same way expected from visible matter alone. These motions provide part of the evidence for dark matter, whose gravitational influence keeps outer regions moving faster than visible mass can explain by itself. Gas clouds also orbit, collide, compress, and shear under the galactic rotation. Spiral structure can trigger waves of crowding that pass through the disk, increasing the density of gas in some regions and encouraging star formation. The galaxy is therefore not a static arrangement of objects but a long-lasting pattern of movement. For habitability on galactic scales, the Milky Way provides both opportunities and hazards. It contains vast numbers of stars, and many of those stars have planets. It also contains energetic events such as supernovae, intense ultraviolet radiation near massive star-forming regions, and dynamical disturbances caused by close passages through dense environments. Conditions vary strongly from place to place. Some regions are richer in planet-building material, some are calmer over long periods, others are more dangerous to atmospheres and biological systems. The overall galaxy is therefore not one single habitat, but a patchwork of environments shaped by density, chemistry, and time. This broad structure makes the Milky Way a plausible home for many kinds of planetary systems. It is old enough for multiple generations of stars and planets to have formed. It is chemically enriched enough in many regions to produce rocky worlds. It is dynamic enough to keep recycling gas and dust into new stars while preserving long-lived stellar populations. At the same time, the galaxy is uneven. Dense central regions, active spiral arms, quiet inter-arm spaces, outer disk territories, and sparse halo paths all offer different balances of stability and risk. As a habitat, the Milky Way is neither uniformly welcoming nor uniformly hostile. It is a layered environment in which the prospects for life depend on location, chemical history, and the long rhythm of galactic change. Across its disk and into its halo, stars move through a structure built over billions of years, carrying with them the materials and conditions that might, in some places, support living worlds and perhaps technological civilizations. The question is not whether the galaxy can host planets, because it plainly can. The quieter scientific question is where within this large system conditions remain most favorable for complexity to persist over long spans of time. Within the broad structure of the Milky Way, conditions are not equally favorable in every direction or at every distance from the galactic center. Astronomers use the phrase galactic habitable zone as a cautious way to describe this unevenness. It does not mean a sharply bounded ring where life must exist, and it does not mean that regions outside it are sterile. It refers instead to a statistical idea. Some parts of a galaxy may offer a better long-term balance between the ingredients needed for rocky planets and the relative calm needed for complex life to persist. One requirement is chemical enrichment. The first generations of stars form in a universe with almost no heavy elements. Over time, stellar fusion and stellar death enrich interstellar gas with carbon, oxygen, silicon, iron, phosphorus, sulfur, magnesium, and many other elements that become part of rocks, atmospheres, oceans, and living systems on Earth. In a galaxy, this enrichment is not uniform. The inner regions generally pass through more rapid cycles of star formation and stellar death, so they accumulate heavy elements earlier and more strongly. Farther out, the outer disk often remains less enriched, especially in earlier epochs. A region with too few heavy elements may still form stars and gas giants, but the formation of abundant rocky planets can be less likely, or may proceed differently. At first glance, the inner galaxy might seem ideal because it is rich in those planet-building materials. Yet the same inner richness brings hazards. The density of stars is higher toward the center, and close encounters between stellar systems, while still rare on human scales, become more probable over billions of years. More important, energetic events are more common in crowded and active regions. Massive stars form in larger numbers where gas is dense, and massive stars live short lives before exploding as supernovae. These explosions release intense radiation and accelerate charged particles. If such an event occurs close enough to a living planet, it can damage atmospheres and increase radiation at the surface. Observations and models indicate that frequency and severity of such hazards rise in denser galactic environments. The very central regions add further complications. Near the nucleus, the concentration of stars, gas, radiation, and gravitational disturbance is high. The supermassive black hole at the center of the Milky Way is quiet at present, but the inner environment has a more active past and a greater potential for energetic phenomena associated with gas inflow, compact objects, and concentrated star formation. For these reasons, many models place the most hostile conditions closer to the galactic center, especially for the long-term stability needed by surface life on Earth-like worlds. Moving outward through the disk, the balance changes. The middle regions of the galaxy appear more moderate. Here, heavy elements are still abundant enough for rocky planets to form in large numbers, but stellar crowding and extreme radiation hazards are generally reduced compared with the innermost zones. The Sun lies in one of these middle regions, at a distance of roughly 26,000 light-years from the galactic center. This location is sometimes treated as broadly representative of a favorable galactic environment, though it must be remembered that one example cannot define a universal rule. The outer disk presents a different balance. Stellar density falls, and some hazards associated with crowding become less frequent. Yet the average abundance of heavy elements also declines. In the far outer reaches of the galaxy, earlier generations of stars may have produced fewer of the elements needed for rocky planets, especially in the deeper past. Even so, observations of exoplanets show that planet formation is robust and varied. Small rocky planets appear around stars with a range of chemical compositions, and the relationship between metallicity, a term astronomers use for the abundance of elements heavier than helium, is not simple for all planet types. Giant planets show a stronger preference for metal-rich stars, while smaller rocky worlds may form in a wider range of settings. This means the outer galaxy cannot be dismissed. It may be less productive on average in some respects, but it is not necessarily barren. Time is part of the galactic habitable zone as much as place. Early in the Milky Way's history, many regions may have been too poor in heavy elements for widespread rocky planet formation, or too active in star formation and supernova rate for long biological stability. As the galaxy ages, the safer and chemically enriched regions can shift. A zone that is favourable at one epoch may differ from a favourable zone billions of years later. The habitable zone of a galaxy is therefore not a permanent map drawn once and fixed forever. It evolves as gas is consumed, stars enrich the medium, and stellar populations change. Another factor is the motion of stars through the disk. A star does not always remain at precisely the same galactic radius over billions of years. Interactions with spiral structure and other dynamical processes can shift stellar orbits inward or outward to some degree. This process, called radial migration, means that a planetary system may experience more than one galactic environment over its lifetime. A star born in a somewhat different region can later orbit where the Sun now does, or move away from its place of origin. Such migration complicates any simple picture of fixed, safe bands. Comets and asteroid reservoirs may also depend on galactic environment. Passing stars and galactic tides can disturb distant icy bodies in a planetary system, sending some inward. A moderate disturbance may increase impacts. Too much disturbance could produce prolonged instability. The frequency of these effects depends partly on local stellar density and on a system's location within the galactic gravitational field. The exact role of galactic environment in shaping impact histories remains an active area of study, but the broader principle is clear: the galaxy influences planetary systems not only through chemistry and radiation, but also through long-term gravitational context. For advanced life and civilization, duration matters. On Earth, complex multicellular life appears only after billions of years of planetary history, and technological civilization emerges much later still. If that pattern is even partly typical, then the most favourable galactic environments are not merely those that can produce planets. They are those that can allow stable conditions over immense stretches of time. This favours regions where destructive events are relatively infrequent and where stars suitable for long-lived habitable planets are common. The galactic habitable zone remains a model, not a settled boundary. Observations indicate broad trends, but many uncertainties remain. Life may prove adaptable to conditions that seem difficult from an Earth-based perspective, and local planetary factors may outweigh galactic background in many cases. A thick atmosphere, a strong magnetic field, active geology, and orbital stability can protect a world even in a less favourable region. A poorly protected world may fail even in a comparatively calm one. What is known is that the Milky Way offers gradients of chemistry, density, and hazard. Those gradients shape probabilities, not certainties. The middle disk therefore emerges as a plausible long-term refuge within the galaxy, neither too poor in heavy elements nor too crowded and violent. It is a region where stars, planets, and time can remain in useful balance. Within such regions, the next question turns from the galaxy as a whole to the kinds of stars themselves, because even in a favourable galactic neighbourhood, the path toward habitability depends on the nature and lifetime of the Sun a planet orbits. Within a favourable part of the Milky Way, not every star offers the same long, steady conditions for life. Stars differ in mass, temperature, brightness, activity, and lifespan, and those differences shape the worlds around them from the beginning. A planet may orbit in a calm Galilean of the galaxy and still face a difficult future if its star is too short-lived, too unstable, or too violent in radiation. For this reason, the search for long-term habitability narrows from galactic regions to stellar populations, and then to the individual kinds of stars most likely to support enduring planetary climates. A star begins as a collapsing region inside a cold molecular cloud. Gravity pulls gas inward. The centre grows denser and hotter, and eventually nuclear fusion starts. From that point onward, the star spends most of its life on what astronomers call the main sequence, a long phase in which hydrogen fuses into helium in the core. The length and character of that phase depend mostly on mass. Massive stars burn their fuel quickly, smaller stars burn it slowly. This simple rule has large consequences. A very massive star can shine brilliantly, but live only millions of years, while a modest star can remain stable for billions or even trillions of years. The most massive stars are poor candidates for life-bearing systems. They emit intense ultraviolet radiation, drive strong stellar winds, and end in supernova explosions after relatively brief lives. Their surrounding disks may form planets, but the available time for biological evolution is short. On Earth, even the simplest life appears to require hundreds of millions of years after conditions become suitable, and complex life takes far longer. A star that lives only a few million years leaves little room for that progression. Its eventual explosion also transforms the surrounding region with radiation and shock waves. Massive stars therefore contribute to galactic chemistry and structure, but they are unlikely to host long-lived biospheres on nearby worlds. Intermediate stars offer a different balance. The Sun belongs to this broad category, though it lies toward the lower mass end compared with brighter, hotter stars like Sirius. A star like the Sun remains on the main sequence for about 10 billion years. This gives planetary systems a wide interval in which climates can settle. Oceans can persist, and evolution can proceed. The Sun is not perfectly constant, but its changes are modest on short timescales and gradual on very long ones. That kind of stability matters, Biological and atmospheric systems can adapt to slow change more easily than to repeated extremes. Slightly larger and hotter stars than the Sun can also host planets, but their lifetimes shorten as mass rises. A star somewhat more massive than the Sun may remain stable for only a few billion years. That may still be enough for life in principle, but the margin becomes smaller. Higher ultraviolet output may also affect atmospheric chemistry and surface conditions. On the other hand, stars somewhat less massive than the Sun often live much longer, extending the available time for habitability. This has led many researchers to consider orange dwarf stars, sometimes called K-type stars, as especially promising. They are smaller and cooler than the Sun, but generally less extreme in magnetic activity than the smallest red dwarfs. They may combine long lifetimes with relatively stable radiation environments. The smallest and most common stars in the Milky Way are red dwarfs. These stars are dim, cool, and extraordinarily long-lived. Many will outlast the current age of the universe by a wide margin because they burn fuel so slowly. At first glance, this seems ideal for life. A long-lived star gives biology an immense amount of time, yet red dwarfs bring their own difficulties. They're habitable zones, the range of distances where a planet could maintain liquid water under suitable atmospheric conditions, lie very close to the star because the star is faint. A planet in that zone may become tidally locked, meaning one side always faces the star while the other always faces away. Tidal locking does not automatically prevent habitability, since a thick atmosphere or ocean can move heat around, but it creates a different climate pattern from Earth's. Young red dwarfs are also often magnetically active. They can produce strong flares and bursts of high-energy radiation. Because habitable zone planets orbit so close, they receive more of this activity. Repeated flaring can erode atmospheres, alter chemistry, and challenge surface life, especially if the planet lacks a protective magnetic field or a sufficiently thick atmosphere. Observations indicate that many red dwarfs remain active for long periods compared with stars like the Sun. It remains uncertain how often planets around these stars can retain habitable conditions over billions of years. The question is open, not settled. Red dwarfs are abundant and many have rocky planets, but abundance alone does not resolve the issue of long-term biological stability. Binary and multiple star systems add another layer of complexity. Many stars form in pairs or larger groups. Planets in such systems can exist, either orbiting one star with the companion farther away or orbiting both stars if the pair is close together. The geometry of these systems affects orbital stability and climate forcing. Some arrangements remain stable for billions of years, while others are chaotic or dynamically hostile to planet formation in certain regions. Since multiple star systems are common, they widen the range of possible planetary environments, but they also remind that a suitable star is not only a matter of mass, it is also a matter of orbital architecture. The age of a star matters as much as its type. Very young stars are often turbulent, their strong winds, high-energy radiation, and leftover disks of gas and dust can make early planetary conditions unstable. Over time, many stars become quieter. This settling phase can allow atmospheres to form or reform, surfaces to cool, and impact rates to decline. A system that is too young may not yet offer lasting calm. A system that is very old may remain habitable if its star is long-lived. But internal planetary processes such as volcanism, magnetic shielding, or carbon cycling may weaken. Habitability is therefore a partnership between star and planet, unfolding through time. Metallicity also influences stellar populations and their planets. Stars that form later in galactic history generally contain more heavy elements than earlier stars. Higher metallicity tends to support the formation of solid grains in protoplanetary disks, which can help build rocky planets. Yet this relationship is not absolute. Small rocky worlds are observed around stars with a range of compositions. What seems most important is that the disk contains enough solid material to assemble planets within the available time. The star provides the energy and the lifetime. But the birth chemistry helps determine what kinds of worlds appear around it. From the perspective of advanced civilization, long-lived stars are especially important. Intelligence and technology may require not only life, but repeated environmental stability across vast stretches of time. A short-lived or highly active star narrows that window. A calmer, longer-lived star widens it. This does not prove that civilizations prefer certain stellar types, because no examples beyond Earth are known. It does suggest that the most probable homes for long-developed societies may orbit stars that avoid extremes and remain stable for billions of years. The Milky Way contains many such stars. Sun-like stars offer one proven template for a habitable world, though only in a single known case. Orange dwarfs may provide an even broader span of stable conditions, while red dwarfs remain an open and important possibility, uncertain because of flare activity and close inhabitable zones. Massive stars, for all their beauty and power, are too brief and too intense to serve as likely long-term cradles for complex life. As attention moves inward from stars themselves, the next step lies in the material around newborn stars, where gas and dust settle into disks and begin the slow work of building planetary systems. Around a young star, the remaining material from its birth does not vanish at once. It settles into a rotating disk of gas and dust, broad, thin, and gradually changing. This protoplanetary disk is the birthplace of planets, moons, asteroids, and comets. Its structure is shaped by gravity, motion, heat, radiation, magnetic effects, and countless collisions among tiny solid grains. The star occupies the center, but the disk holds the future architecture of the system. Within it, matter is sorted by distance, temperature, and time. The disk forms because collapsing gas carries angular momentum, the tendency of a rotating system to keep rotating. As the cloud contracts, that rotation becomes faster, and in falling material cannot drop straight into the center. Instead, it spreads into a flattened disk around the young star. Most of the mass is gas, mainly hydrogen and helium. Only a small fraction is dust, made of heavier elements and compounds such as silicates, metals, and carbon-rich grains. Yet that small fraction is crucial, because rocky bodies begin as solids. Temperature changes strongly with distance from the star. Close to the star, heat is intense. Volatile materials, which are substances that evaporate easily, cannot remain solid for long. Water, carbon dioxide, methane, and ammonia tend to exist as gas in these hotter inner regions, while only more refractory materials, meaning heat-resistant solids such as silicate minerals and metals, remain stable, farther out. Where the disk is colder, volatile compounds can freeze into ice. This transition is often called the snow line, though its exact distance depends on the brightness of the young star and on conditions in the disk. The snow line matters because ice adds a large amount of solid material. Beyond it, planetary building can proceed with more raw mass. At first, the solid grains are microscopic. They drift through the gas, collide gently, and sometimes stick through electrostatic forces and surface effects. Over time they grow into larger aggregates, then into pebbles, and then into bodies large enough for gravity to matter more strongly. This growth is not smooth or guaranteed. Some collisions lead to sticking, some to bouncing, and some to fragmentation. Gas drag also affects the motion of growing solids, causing them to spiral inward under some conditions. The path from dust grain to planet is therefore a competition between growth and loss. As bodies grow into kilometre-scale planetesimals, gravity becomes an important force in further assembly. A planetesimal is a small early building block of planets, large enough that its own gravity influences nearby material. Swarms of these bodies orbit within the disk, colliding, merging, and sometimes breaking apart. In regions where growth outpaces destruction, larger objects emerge. These become planetary embryos, bodies that dominate their local neighborhoods and pull in surrounding material more efficiently. The pace of this process depends on local density, collision speed, disk lifetime, and distance from the star. The gas itself does not remain forever. Young stars emit radiation and winds that gradually disperse the disk. Observations indicate that many protoplanetary disks survive only a few million years, though some last longer and some fade sooner. This limited lifetime is important. Giant planets that need large envelopes of hydrogen and helium must gather them before the gas is lost. Rocky planets, built mostly from solids, can continue accreting after much of the gas has gone, but their early environments are still shaped by that gaseous phase. The timing of growth therefore affects the kinds of planets that a system can produce. In the inner disk, where temperatures are high and ices are scarce, the available solid material is more limited. Planets forming here tend to be rocky and comparatively smaller, because they build from silicates and metals without the large contribution of frozen volatiles. Mercury, Venus, Earth, and Mars reflect this pattern in the solar system. Beyond the snow line, the larger reservoir of solids can help planetary cores grow rapidly. If a core becomes massive enough while gas is still present, it may capture a thick atmosphere and become a gas giant or an ice giant, depending on mass and composition. Jupiter and Saturn contain large amounts of hydrogen and helium, while Uranus and Neptune contain more heavy volatile substances mixed with gas. Observations of other systems show that many architectures are possible, including arrangements unlike the solar system. Migration can reshape a forming planetary system. A young planet interacts gravitationally with the surrounding gas disk, and these interactions can move the planet inward or outward. Small and medium planets may drift significantly over time. Giant planets can also migrate, sometimes moving close to their stars. This process helps explain the existence of hot Jupiters, giant planets found on very tight orbits around other stars. Such planets likely form farther out and later move inward. Migration affects the fate of smaller bodies as well. A migrating giant planet can scatter or consume material, alter collision rates, and disrupt or encourage the growth of rocky worlds depending on timing and path. This means a planetary system is not simply built in place, it may be rearranged while still young. Water and other volatile materials reach inner rocky planets through more than one route. Some water may be incorporated directly if the local disk conditions permit hydrated minerals or if the snow line shifts over time. Additional delivery can occur through impacts by water-rich planetesimals from somewhat colder regions farther out. In the solar system, the origin of Earth's water is still studied, with evidence pointing to contributions from several sources, including primitive asteroidal material. The exact balance remains uncertain. what is clear is that the final composition of a rocky planet depends not only on where it forms, but also on the dynamical mixing of the disk. The young system is often violent. Collisions between embryos can be immense, melting crusts, stripping atmospheres, and altering rotation. The Moon is thought to form after such a giant impact between the early Earth and a Mars-sized body. Similar collisions are expected in many systems. They are part of planetary assembly, not an exception. Through repeated impacts and mergers, the number of bodies declines while the survivors grow larger and more distinct. Some systems may stabilize with several rocky planets, others may retain belts of debris, scattered remnants, or strongly eccentric orbits. Order emerges slowly from a crowded beginning. Chemical gradients in the disk also influence planetary diversity. Regions differ in temperature, oxidation state, ice content, and dust abundance. These differences affect mineralogy, core formation, and atmospheric ingredients. A planet that forms slightly closer to the star may become dry and metal-rich. One farther out may retain more water or volatile compounds. Even planets around the same star can therefore follow very different histories from the earlier stage. The disk is one system, but it does not produce identical outcomes. By the time the gas clears, the broad blueprint of the planetary system is largely set, though evolution continues through impacts, cooling, atmospheric loss, and orbital adjustment. The star now shines on worlds that begin as products of dust, ice, collision, and time. Some are barren, some are giant, some are unstable, and some may settle into long-lived orbits where liquid water can exist on the surface or below it. The diversity seen among exoplanets today reflects the many ways a disk can distribute matter and the many ways gravity can rearrange it before the system reaches maturity. Planetary systems therefore arise as natural outcomes of star formation. They are not rare accidents added afterward, but part of the same continuous process that turns clouds into suns. Gas and dust around young stars provide the setting, and within that setting, physics builds a wide range of worlds. The next step inward is not the disk itself, but the particular planets that emerge from it, especially the rocky worlds where water, air, and chemistry may combine into conditions that life can use. Among the many worlds that form around stars, only a small fraction are likely to combine the conditions that life as known on Earth appears to require. A world does not become promising merely by being rocky or by orbiting at a moderate distance from its star. Habitability depends on a network of properties that act together over long periods. These include size, composition, atmosphere, water, internal heat, magnetic shielding, orbital stability, and the behavior of the host star. Each factor can support or weaken the others. A planet that succeeds in one respect may fail in another. The result is not a single recipe, but a narrow and complex range of possibilities. A rocky planet is one made primarily of silicate rock and metal rather than deep layers of gas. Such a planet needs enough mass to hold an atmosphere and maintain internal heat, but not so much that it becomes a gas-rich body of an entirely different kind. If the mass is too small, gravity is weak, volcanic and tectonic activity may decline quickly, and atmospheric gases can escape more easily into space. Mars shows some of these limits. It preserves evidence of ancient water flow, yet its small size contributes to atmospheric thinning and long-term surface drying. If a rocky planet is larger than Earth, it may retain a thicker atmosphere and stronger gravity, but the consequences for climate, geology, and ocean depth can vary. A more massive rocky world, often called a super-Earth, is not automatically more habitable. It is simply different, and its surface conditions depend on many linked processes. Liquid water remains one of the most useful guides because all known life depends on it. Water dissolves substances, supports chemical reactions, transports heat, and allows complex molecules to move and interact. For liquid water to persist on a surface, temperature and pressure must fall within a certain range. This is why astronomers speak of the habitable zone around a star, the region where a planet with suitable atmospheric conditions could maintain surface liquid water. The habitable zone is not a guarantee. It is a rough thermal region, not a verdict on biology. Venus lies near the inner side of the Sun's habitable zone, but has a surface hot enough to melt lead because its dense carbon dioxide atmosphere drives an extreme greenhouse effect. Mars lies near the outer side but is cold and dry at the surface today because its atmosphere is thin. Earth occupies a middle case where atmosphere, water, geology, and incoming sunlight remain in a balanced state over long timescales. Atmospheres do more than set temperature. They regulate pressure, transport heat, filter harmful radiation, and provide the chemical setting for climate and surface reactions. A thick atmosphere can keep a planet warm, sometimes too warm. A thin atmosphere may fail to prevent water from freezing or evaporating away over time. The composition matters greatly. Carbon dioxide, water vapor, and methane are greenhouse gases, meaning they trap outgoing heat. Nitrogen, though not a strong greenhouse gas, can help maintain pressure and broaden the climate range where liquid water is stable. Clouds can either cool a planet by reflecting starlight or warm it by trapping heat, depending on altitude, thickness, and composition. Habitability, therefore, depends on atmospheric evolution, not just atmospheric presence. A planet's interior also matters. Internal heat, supplied by leftover formation energy, gravitational settling, and the radioactive decay of elements, powers volcanic activity and mantle motion. On Earth, geology supports the long carbon cycle that helps stabilize climate. Carbon dioxide enters the atmosphere through volcanic release and is removed through weathering and burial, then returned by geological processes over very long times. This cycle is not simple, but it helps prevent climate from running permanently to extremes. Without internal activity, a planet may lose part of its ability to recycle crucial gases and maintain long-term climate balance. Plate tectonics, the large-scale movement of crustal plates, is one way this can happen, though it remains uncertain whether Earth-style plate tectonics is necessary for life everywhere. It is the only confirmed example of a planetary climate regulator of this depth and duration. Magnetic fields may add protection, though their exact importance is still studied. A strong global magnetic field can deflect charged particles from stellar winds and reduce some forms of atmospheric erosion. Earth's field performs this role. Mars, by contrast, lacks a present-day global magnetic field, and its atmosphere has been more exposed to solar winds stripping over geological time. Even so, a magnetic field is not a simple shield that guarantees safety, nor does the absence of one guarantee failure. A thick atmosphere can still provide substantial protection, and many details depend on the strength of the stellar wind and the composition of the upper atmosphere. What observations indicate is that magnetic protection may help some planets preserve habitable surface conditions over long periods. Orbit and rotation shape climate as well. A planet on a nearly circular orbit receives more even energy through its year than one on a highly elongated path. Large swings in distance from the star can drive strong seasonal extremes. Rotation rate influences day length, atmospheric circulation, and temperature contrast between day and night. Axial tilt affects seasons. A moderate tilt can support climate variety without severe instability, while extreme tilts may produce more dramatic patterns of warming and cooling. Moons can sometimes stabilize planetary tilt, as Earth's moon is thought to help do. Without such stabilization, the axis of a planet may vary more chaotically over long intervals. These orbital and rotational factors do not determine habitability alone, but they help define whether a climate remains steady enough for complex systems to persist. Water itself can appear in very different amounts. A planet may be dry, with only scattered reservoirs. It may resemble Earth, with oceans and continents sharing the surface. Or it may become a water world, covered by deep global oceans. A great abundance of water is not automatically ideal. If oceans are extremely deep, high-pressure ice may form at the bottom and isolate the water from rocky seafloor material, limiting useful chemical exchange. Continents may also play roles in nutrient cycling and climate regulation. These questions remain open. Earth provides one functioning example with both land and sea, but other arrangements may also support life under the right conditions, beyond planets themselves. Some moons may also be habitable in limited or subsurface ways. In the solar system, Europa and Enceladus hold global oceans beneath ice, warmed partly by tidal heating. Tidal heating occurs when gravitational flexing inside a moon generates heat. These worlds do not sit within ordinary surface habitable conditions, yet they show that liquid water can persist even far from a star if another energy source exists. Subsurface oceans widen the concept of habitability, though whether such environments commonly produce life remains unknown. For technological civilization, surface habitability may still be more favorable because open air, visible skies, and accessible energy flows could matter. But this remains an inference rather than a demonstrated rule. Exoplanet observations reveal that small rocky planets are common. Many orbit within the broad habitable zones of their stars, yet most important details remain difficult to measure. Astronomers can often determine orbital period, rough size, and sometimes mass. From these, density can be estimated, which helps distinguish rocky worlds from gas-rich ones. Atmospheres are much harder to characterize, especially for Earth-sized planets. Observations indicate possibilities, but certainty is rare. A world may look promising in size and orbit while still proving dry, airless, or chemically hostile. Worlds that could host life therefore form a subset within the wider population of planets. They are shaped by their stars, their birth materials, their internal engines, and their long climate history. Rocky composition, liquid water, and a suitable atmosphere are central, but none acts alone. Habitability is a moving balance maintained over immense stretches of time. The galaxy likely contains many worlds that approach this balance, and perhaps some that achieve it more securely than Earth. Yet whether any such world actually develops life, and whether life then grows into complexity and intelligence, depends on a further layer of time that no telescope can measure directly from a planet's surface alone. A world may possess rock, water, air, and long periods of physical stability, yet still remain lifeless. Habitability describes the capacity to support life, not the certainty that life begins. Between a suitable planet and a technological civilization lies a span of history that is still understood through only one confirmed example. Earth provides the sole complete record, and from that record one broad fact stands out with unusual clarity: the path from a young habitable planet to intelligent tool-using beings is long. It extends across billions of years, and each major transition appears to depend on earlier layers of chemistry, environment, and biological change. Earth forms about 4.5 billion years ago. The early planet is hot, heavily bombarded, and still differentiating internally, meaning dense material sinks toward the core while lighter material remains above. Over time, the surface cools enough for stable crust to form and for liquid water to gather. The oldest evidence consistent with life appears surprisingly early in geological terms, within the first billion years of Earth's history and perhaps earlier, though the exact timing remains uncertain, because the oldest rocks are rare and altered. Observations indicate that simple life emerges relatively soon after conditions become permissive, at least on this planet. What remains uncertain is whether this means life begins easily wherever chemistry allows, or whether Earth records a rare success that happened early by chance. The first living systems are microscopic. They do not possess organs, nervous systems, or even the internal complexity of later cells. Yet they already represent a major threshold. Life requires a boundary that separates an organism from its surroundings, a way to store and copy information, and a metabolism that draws energy from the environment to maintain internal order. How non-living chemistry first crosses into this state remains unresolved. Several lines of research study hydrothermal settings, shallow water environments, mineral surfaces, and cycles of wetting, drying, heating, and cooling. Laboratory work shows that some building blocks of life can arise from plausible prebiotic chemistry, and that molecules important for heredity and metabolism can form under a range of conditions. Still, the exact route from chemistry to the first true cells is not known. Observations indicate that life is ancient on Earth. It remains uncertain how common the origin process is elsewhere. For a very long time after life begins, Earth remains a microbial world. Simple organisms dominate oceans and sediments, and they reshape the planet in gradual ways. Among the most important changes is the rise of oxygen-producing photosynthesis, a process in which light energy is used to split water and build organic matter while releasing oxygen. This innovation likely evolves in microbial lineages long before atmospheric oxygen accumulates to high levels. The delay matters. Oxygen released into the environment is first consumed by dissolved iron, volcanic gases, and other reduced materials. Only after these sinks are partly saturated does oxygen begin to build more substantially in the atmosphere. This major transition, often called the Great Oxidation Event, occurs more than 2 billion years ago. It transforms planetary chemistry, alters climate, and opens ecological possibilities for more energy-rich forms of metabolism. Even then, complexity does not rise quickly. Complex cells, known as eukaryotic cells, appear after a long earlier age dominated by simpler cells. Eukaryotes contain internal compartments and structures, including a nucleus, and they likely arise through a symbiotic merger in which one cell takes up another and retains it. Mitochondria. The energy-producing parts of modern complex cells are understood to descend from such an ancient partnership. This transition is profound because it allows larger cell size, greater internal organization, and more flexible control of energy. Yet it takes a large portion of Earth's history to appear, and after it appears, multicellular organisms still remain far in the future. Multicellularity evolves more than once in Earth's history, but large complex bodies become widespread only much later. For most of the planet's timeline, even after oxygen becomes more available, life remains small. The reasons are still studied: environmental stability, oxygen levels, nutrient availability, ecological feedbacks, and chance evolutionary pathways may all play roles. By the late Precambrian, multicellular organisms become more evident, and during the Cambrian period, animal body plans diversify rapidly on geological timescales. Rapidly here still means millions of years. Evolution does not move with intention or toward a fixed goal. It works through variation, inheritance, and selection, with contingency shaping which lineages persist and which vanish. Intelligence, as seen in humans, appears much later and is not the inevitable culmination of evolution. Many successful organisms never develop anything close to human cognition. Earth supports abundant life for hundreds of millions of years before vertebrates appear, and vertebrates exist for a long time before mammals become prominent. Primates arise late. The lineage leading to humans separates from that of chimpanzees only within the last several million years. Anatomically modern humans appear very recently relative to the age of life as a whole. Tool use, symbolic behavior, large-scale cooperation, and technological culture are layered developments within this already late lineage. The lesson from Earth is not that intelligence is impossible. It is that intelligence capable of engineering is not an early or guaranteed outcome. Mass extinctions also shape the timetable. Earth's history includes repeated crises triggered by impacts, volcanism, climate change, ocean chemistry shifts, and other large disturbances. These events remove many lineages and open opportunities for others. The extinction at the end of the Cretaceous period eliminates non-avian dinosaurs and allows mammals to diversify more broadly in the aftermath. Without such contingent events, the later rise of humans might not occur in the same way or at all. This does not mean intelligence depends on catastrophe, only that biological history is deeply path-dependent. Small differences in timing or environment can lead evolution along different branches. For evaluating other worlds, the main scientific difficulty is the sample size of one. Earth suggests that life may emerge relatively early once conditions allow, but complex multicellular life takes much longer, and technological intelligence appears later still. One interpretation is that the origin of life is common while later steps are rare or slow. Another is that all steps may be common given enough time, and Earth simply shows the minimum broad sequence. At present, observations cannot distinguish these possibilities. No confirmed biosignature has yet been measured on an exoplanet, and no independent life has been found elsewhere in the solar system. The timescale problem therefore remains open. Star lifetime becomes crucial here. If complex life often takes billions of years, then stars that remain stable over such spans become especially important. A planet around a short-lived or highly variable star may lose its opportunity before intelligence can evolve. Likewise, planetary stability must last for long intervals without sterilizing impacts, extreme climate collapse, or atmospheric loss. A habitable world is not enough. It must remain habitable, or at least recoverable, through deep time. There is also the possibility that many biospheres never move beyond microbial life. Microbes are adaptable, ancient, and resilient. They occupy an enormous range of environments on Earth, from deep crust to polar ice to acidic hot springs. If simple life begins elsewhere, it may persist without producing animals, forests, or civilizations. The universe may contain many living worlds that never become visible across interstellar distances because they never produce technology. This is plausible, but it remains unproven. What Earth shows most clearly is duration. From the first likely signs of life to the rise of a technological species, nearly the whole age of the planet is used. This makes time one of the most important ingredients in the story. A civilization capable of interstellar engineering would need not only a habitable planet and a suitable star, but also a very long, uninterrupted chain of biological and cultural continuity. Worlds that possess these ingredients may exist, but Earth's records suggest that such worlds would be the product of patience, measured not in centuries or millennia, but in billions of years. After intelligence appears in a biological lineage, technology does not arise all at once. It grows from a sequence of capacities that depend on body form, memory, learning, social structure, and access to usable energy and materials. A species may be intelligent in many meaningful ways and still never develop machines, astronomy, or large-scale engineering. On Earth, many animals solve problems, communicate, cooperate, and alter their surroundings. Yet only one lineage builds cumulative technological culture strong enough to reshape the planet. This suggests that intelligence alone is not the threshold. The crucial transition is the rise of a civilization that stores knowledge outside individual minds, improves tools across generations, and learns to control energy beyond immediate biological needs. Humans provide the only known example. Anatomically, modern humans appear in the recent geological past, but for most of that time, daily life is organized around hunting, gathering, small groups, and local ecological knowledge. These societies are fully human in cognition and culture, yet their technological reach remains limited by available materials, population density, and energy capture. Over long spans, stone tools improve, fire is controlled, symbolic communication deepens, and social learning becomes increasingly powerful. Still, the environment remains the primary source of direct constraint. The step towards civilization in the stronger sense begins when knowledge accumulation, food surplus, and settled life allow specialization. Agriculture changes this balance by concentrating energy flow from landscapes into stored food. This supports larger populations, permanent settlements, and divisions of labor. Once some members of a society can spend less time obtaining food, more time becomes available for craft, administration, mathematics, record keeping, and later formal science. Written language is one of the most important amplifiers in this process. It allows information to persist beyond memory and beyond the lifespan of individuals. Measured observations, technical procedures, and institutional knowledge can now accumulate. A technological civilization is therefore not simply a group with tools. It is a system that preserves and extends knowledge through time. Metallurgy deepens this process by giving societies access to materials with controlled properties. Stone, wood, bone, and fiber remain useful, but metals allow sharper edges, stronger structures, and more precise devices. Over centuries and millennia, engineering expands from hand tools to water power, wind power, mechanical clocks, lenses, and navigation techniques. These developments do not yet place a civilization among the stars, but they mark a widening command of matter and energy. The transition to industrial society then accelerates the pattern. Fossil fuels release ancient stored solar energy in concentrated form. Coal, oil, and natural gas power machines, transport, chemistry, and eventually electricity generation on vast scales. Energy use per person rises sharply, and with it the capacity to mine, build, communicate, and modify landscapes. This rise has a planetary signature. Atmospheric composition changes as carbon long buried underground returns to the air as carbon dioxide. Nitrogen cycles are altered through industrial fertilizer production. Forest cover changes. Species are moved across continents, and artificial night lighting spreads. Radio transmissions begin leaking from Earth into space. Satellites appear in orbit. Surface minerals are redistributed by mining and construction. From an astronomical perspective, a technological civilization becomes not only a social phenomenon, but also a geophysical one. It leaves traces in air, land, ocean, and electromagnetic output. Science transforms technology from local craft into systematic inquiry. Once a civilization develops reliable methods for measurement, experiment, and mathematical description, it can move beyond imitation and tradition toward prediction and control. This allows engines, chemistry, electronics, nuclear physics, and eventually spaceflight. The significance of science is not that it makes progress inevitable. It is that it creates a disciplined way to extract stable regularities from nature and apply them. A civilization with this ability can estimate the age of stars, map planets around other suns, and calculate trajectories between worlds. It begins to understand its place in the galaxy. Energy remains central at every stage. Biological bodies use chemical energy in food. Pre-industrial societies add firewood, animal labor, water, and wind. Industrial societies multiply available energy by tapping fossil carbon and later nuclear reactions and large electrical networks. As energy access rises, so does the possible scale of technological action. A civilization that contemplates interstellar travel would need energy systems far beyond those used for ordinary transport or communication on a single planet. Even robotic probes sent to nearby stars would require precise engineering, durable materials, and substantial energy investment. The path towards such projects begins long before launch. It begins when a civilization reaches a level of surplus, coordination, and technical depth that makes very long-term planning possible. This transition is narrow in time when measured against planetary history. On Earth, radio technology, powered flight, and orbital launch all emerge within a tiny fraction of the age of the planet. That narrowness matters because it suggests that the detectable technological phase of a civilization may begin suddenly in geological terms. A world may remain biologically quiet for billions of years and then acquire radio leakage, industrial emissions, and satellites within only a few centuries. This creates an observational challenge. If technological phases are brief, then even a galaxy with many living worlds may contain only a small number of civilizations detectable at the same time. There are also limits and dangers internal to civilization. Technology increases power, but it also increases the scale of self-inflicted risk. Environmental degradation, climate change, war, resource depletion, engineered pathogens, and uncontrolled artificial systems are all examples of pressures that a sufficiently advanced society may create for itself. Earth shows that industrial civilization can alter planetary systems quickly, sometimes faster than social institutions adapt. A technological species therefore faces a difficult passage. It must survive the period in which its ability to disrupt its environment grows faster than its ability to govern that disruption. Whether most civilizations pass this stage, stall within it, or fail because of it is unknown. Longevity matters more than peak capability. A civilization that becomes highly advanced for only a few centuries may leave little enduring mark beyond its planet. A civilization that remains stable and cumulative for tens of thousands or millions of years could spread artifacts, probes, or engineered signals across large parts of a stellar neighborhood. The important variable for interstellar consequences is not only intelligence or energy use, it is persistence. A patient civilization with moderate but sustained capability may achieve more across cosmic distances than a brilliant but short-lived one. Cultural choices also influence technological direction. A civilization may possess the means for certain projects and still decline to undertake them. It may focus inward on virtual environments, ecological balance, local exploration, or forms of existence that require little outward expansion. It may automate much of its activity through machines, sending robotic systems where biological bodies are fragile. Since no extraterrestrial civilization is known, these possibilities remain speculative. What can be said more firmly is that technology opens multiple paths. It does not force one universal destiny. From the standpoint of astronomy, the rise of a technological civilization marks the moment when a biosphere becomes, in principle, visible across space. Its planet may show industrial atmospheric gases, artificial radio output, or energy use that departs from purely biological patterns. Yet Earth also shows how subtle such signs can be. Even now, many of the strongest signatures are faint over interstellar distances. A civilization can transform its own world and still be hard to detect from far away. Detectability depends on scale, duration, and the kind of technology used. The rise of technology therefore narrows the field from living planets to communicating or engineering societies. It requires a long chain of earlier successes: stable stars, habitable worlds, persistent life, complex cells, multicellular organisms, intelligence, culture, energy mastery, and durable institutions. Each link may be common or rare. Present science cannot say. What is clear is that once such a civilization exists, it begins to alter its planet in measurable ways and acquires the potential, though not the certainty, to project some part of itself beyond its home world. Once a technological civilization begins to alter its world, astronomers can ask a practical question: which changes might be visible across interstellar distances? The answer depends less on imagination than on signal strength, duration, and contrast with natural processes. A civilization may build cities, machines, and networks across an entire planet and still remain almost invisible from far away if those activities do not produce a strong, distinctive mark. Detectability is not the same as existence. A world may host intelligence and yet offer no clear sign that current instruments can isolate. One of the earliest ideas is radio communication. Radio waves pass through space efficiently, and human civilization has produced them for more than a century. For a time, this seems like a natural way to search for intelligence. If another society uses radio for communication, radar, navigation, or astronomy, some part of that signal might escape its planet and travel outward. The difficulty is that ordinary leakage weakens quickly with distance. Power spreads over an ever larger sphere, and by the time a faint signal reaches another star system, it may be buried beneath natural background noise unless it is very strong or deliberately directed. Earth's own accidental radio leakage becomes difficult to detect at even modest interstellar distances with present assumptions about receiving systems. A narrow, intentional beacon would be easier to detect than casual leakage, but there is no evidence that any such beacon has been confirmed. Searches for radio signals have therefore focused on patterns unlikely to be produced by nature. A narrow-band signal, concentrated into a very small range of frequencies, is one classic example because most natural radio sources are broader. Repetition, modulation, and unusual drift patterns may also stand out. Over decades, many searches have scanned stars, parts of the galactic plane, and nearby galaxies across selected frequency ranges. Some transient candidate signals have appeared, but none has remained reproducible and confirmed as artificial after follow-up study. This absence does not show that no technological civilization exists. It means only that no verified radio signature has yet risen clearly above uncertainty. Optical and infrared searches extend the same logic into other parts of the spectrum. A civilization might use powerful lasers for communication or for other purposes, producing brief flashes or steady beams distinguishable from ordinary starlight. Lasers can be highly directional, which helps a sender concentrate energy, but that same directionality also reduces the chance that another world lies in the beam unless the transmission is aimed. Searches for unusual optical pulses or continuous narrow spectral features have so far found no confirmed extraterrestrial source. Again, the silence is informative but limited. It constrains some kinds of signals more than others. Planets themselves may carry detectable atmospheric signs. This area has grown rapidly with exoplanet astronomy. When a planet passes in front of its star, some of the starlight filters through the atmosphere, allowing astronomers to infer the presence of certain gases. On Earth, life strongly affects atmospheric composition, especially through oxygen and methane, though interpretation is not simple. A technological civilization could add further gases that are rare in nature, especially complex industrial compounds with no obvious biological or volcanic source. In principle, such technosignatures, signs of technology rather than life in general, could reveal an industrial world. In practice, Earth-sized planets are small, and their atmospheres are thin compared with the glare of the host star. Current and near-term observations can probe some atmospheres, but clear identification of weak industrial gases on a distant Earth-like planet remains very challenging. Waste heat offers another possible sign. Any large-scale use of energy eventually ends as heat. This is a basic consequence of thermodynamics. A civilization that captures a substantial fraction of the energy of its star, or uses immense artificial power on planets and in space, should re-radiate much of that energy as infrared emission. This idea leads to searches for stars or galaxies with too much mid-infrared output relative to what natural dust, star formation, or ordinary astrophysical processes would predict. Some studies have looked for evidence of very large astroengineering, such as swarms of structures orbiting a star and intercepting part of its light. Such a swarm would not need to be a solid shell. It would simply have to block some starlight and re-emit the energy at longer wavelengths. So far, observations have found many natural explanations for unusual infrared sources, including dust, young stars, and active galactic nuclei, but no confirmed case of large-scale extraterrestrial engineering. Unusual transit behavior can also attract attention. If a large artificial structure passes in front of a star, the dip in brightness might differ from the shape expected for a normal planet. Irregular timing, complex partial dimming, or wavelength patterns inconsistent with a planetary atmosphere could suggest something else. Yet stars and their environments produce many strange signals naturally. Dust clouds, debris fields, rings, comets, and stellar variability can all create light curves that first appear puzzling. Careful work is required before any unusual dimming is treated as evidence of technology. Up to now, natural explanations have remained sufficient for known cases. There are more indirect possibilities. A civilization could alter the night side brightness of a planet through artificial illumination, though this would be extremely faint from interstellar distances. It could change the spectral reflectance of a world through large-scale agriculture, city surfaces, or solar collectors. It could launch probes that leave chemical traces in a stellar system, or construct machines that modulate starlight in deliberate mathematical patterns. These are all conceivable techno-signatures, but most remain far beyond present detection capability except in special circumstances. Astronomy is often limited not by imagination, but by sensitivity. The search is also shaped by timescale. A biosignature such as atmospheric oxygen may persist for millions or billions of years if life maintains it. A technosignature may be more fragile. Radio leakage can fade as communications technology changes. Industrial gases can disappear if industry stops or becomes cleaner. Large engineering may endure longer, but even that depends on maintenance and purpose. This means a civilization could exist, become detectable, and then become quiet again while leaving little obvious mark to distant observers. The overlap between two civilizations being detectable at the same time may therefore be small even if life is not rare. Another difficulty is that natural astrophysics is rich and varied. Pulsars were once briefly considered possible artificial sources because of their regular radio pulses, but they proved to be rotating neutron stars. Fast radio bursts are intense and mysterious at first discovery. Yet observations increasingly tie them to extreme natural environments involving compact objects. Planetary atmospheres can also mimic or mask biological and technological gases through photochemistry, volcanism, and escape processes. Every candidate signal must be tested against nature first because nature provides many complex patterns without any need for intelligence. For this reason, confirmation standards are high. A true technosignature would need to be reproducible, well characterized, and resistant to plausible natural explanation. Ideally, it would show multiple lines of evidence at once. A narrowband radio signal from a star with an unusual atmospheric spectrum would be stronger evidence than either clue alone. Repetition matters. Independent detection matters. Instrumental error must be excluded. Human interference must also be ruled out, since Earth itself is a strong source of artificial signals that can confuse observations. The scientific picture at present is therefore quiet but not empty. Searches have grown broader and more systematic. Thousands of exoplanets are known. Radio and optical surveys continue. Infrared catalogues have been examined for excess heat and large-scale anomalies. These efforts have not produced a verified detection of extraterrestrial technology. Observations indicate absence of confirmed evidence, not evidence of absence. That distinction matters. It leaves open the possibility that technological civilizations are rare, distant, short-lived, subtle, or using methods not yet searched effectively. Detectable signs across space are thus possible in principle, but difficult in practice. Radio, lasers, atmospheric pollutants, waste heat, and unusual light curves each offer a window. Yet each window is narrow and clouded by distance and natural confusion. A civilization may exist and remain hidden simply because its activity does not project a strong contrast into space. To move from detection to arrival, another problem emerges, more severe than signal weakness. Even if an advanced civilization exists somewhere among the stars, the physical act of crossing the space between one system and another faces the full weight of distance, energy, radiation, and time. Between one star and the next, the emptiness is not complete, but it is vast enough that travel becomes a problem of extreme scale. Inside a planetary system, distances are measured in light minutes or light hours. Between stars, they are measured in light years. A light year is the distance light travels in 1 year, and since light moves faster than any known material object can move, this unit already contains the central difficulty. Even the nearest star system beyond the Sun lies more than 4 light-years away. For a spacecraft moving far below the speed of light, that distance becomes a journey lasting decades, centuries, or longer. For more distant stars, the times grow correspondingly larger. Known physics sets a clear limit. According to relativity, no object with mass can be accelerated to the speed of light. As speed rises closer to that limit, the energy required increases steeply. This does not mean fast interstellar travel is forbidden in principle, but it does mean that every gain in speed becomes expensive. A craft moving at a modest fraction of the speed of light would already require enormous energy compared with present human technology. The energy must not only accelerate the craft, it must also, in most mission designs, guide it, protect it, and possibly slow it at the destination. The faster the journey, the more severe these demands become. Propulsion is therefore the first great barrier. Chemical rockets, the kind used to leave Earth today, are effective for reaching orbit and crossing parts of the solar system, but they are inadequate for practical travel between stars. Their exhaust speeds are too low, and they would require impossible amounts of propellant to accelerate a large payload to interstellar velocity. Nuclear propulsion offers more energetic options. Fission and fusion release far more energy per unit mass than chemistry, and both have been studied as possible routes to high-speed probes or crewed craft. Yet these concepts still face major engineering difficulties involving reactor design, fuel handling, heat management, thrust control, and mission duration. Antimatter, if it could be produced and stored in large quantities, would offer even greater energy density. But present production rates are tiny, and storage is extremely difficult. Theoretical promise does not remove practical barriers. Even if propulsion were solved, interstellar space remains hazardous at high speed. The medium between stars contains very thin gas, magnetic fields, cosmic rays, and small particles of dust. At ordinary speeds within a planetary system, these are minor concerns. At a significant fraction of the speed of light, they become serious. A grain of dust striking a spacecraft at such velocity carries destructive kinetic energy. Shielding can reduce this threat, but shielding adds mass, and mass increases propulsion demands. Radiation also becomes more difficult as speed rises. High-energy particles from space can damage electronics, degrade materials, and harm biological tissue. Long missions would need robust protection, redundancy, and repair capacity. Time itself forms another barrier. A robotic probe may endure a journey lasting centuries if designed for long-term autonomy, though reliability over such spans is a major challenge. A biological crew faces much harder limits. Human bodies need air, water, food, temperature control, waste recycling, protection from radiation, protection from prolonged weightlessness or artificial gravity substitutes, and medical care. The mission must survive not only technical wear but also biological and social continuity. On journeys lasting generations, the original travellers may never see the destination. A generation ship, a vessel in which descendants of the launch population continue the mission, is one conceivable response. But it adds profound difficulties in ecology, governance, psychology, and closed system stability. A civilization capable of building such a craft would need not only engineering skill, but also unusual long-term social coordination. Relativity softens part of the time problem, but only from the traveller's perspective at extremely high speed. As a craft approaches the speed of light, time passes more slowly aboard relative to outside observers. This effect, called time dilation, is measured and well established. In principle, it means a traveller moving very fast could cross large distances while aging less than stationary observers would expect. Yet this does not remove the energy challenge. It makes rapid journeys physically consistent with relativity, but only if the craft can be accelerated to the speeds and survive the conditions encountered there. For outside civilizations waiting at the point of departure or arrival, the full travel time in their frame still passes. Stopping is as important as starting. A spacecraft that reaches another star at high speed does not automatically become useful there. Without a way to decelerate, it may only perform a rapid flyby. Slowing down requires energy and often propellant. Unless the craft can use external methods such as magnetic sails, light sails interacting with radiation, or drag against ambient plasma, all of which come with their own limitations. This is one reason why many realistic interstellar concepts focus on small probes rather than large settlements. A lightweight probe can tolerate higher acceleration, may require less energy, and can send back data without supporting a living crew. Even so, the technical challenge remains formidable. Communication adds further delay. A message from a probe at another star still returns at the speed of light. If the destination lies 10 light-years away, a simple exchange of information takes decades even after arrival. Control from the homeworld becomes increasingly impractical with distance. Interstellar missions therefore require autonomy. The craft must navigate, respond to damage, interpret local conditions, and complete objectives without immediate guidance. Advanced automation or machine intelligence would likely be essential. This suggests that if any civilization undertakes interstellar expansion, its first arrivals may be robotic rather than biological. There are also thermal problems. Powerful engines produce waste heat, and in space there is no air to carry heat away by convection. A spacecraft must radiate its excess energy through surfaces, which means radiator systems can become large and vulnerable. High-power propulsion, onboard industry, or life support all generate heat that must be managed carefully. The faster and more capable the ship, the more serious this issue becomes. Space is cold, but cooling is not easy when vacuum offers no direct medium for heat transfer except radiation. Resource economics create a further limit. Even if a civilization can build one interstellar craft, doing so repeatedly at large scale may remain expensive. The cost is not only energy, it includes materials, industrial infrastructure, skilled labor or advanced automation, launch facilities, and long-term support systems. A society may decide that remote sensing, robotic exploration within its own system, or digital forms of existence are more efficient than spreading physically across the stars. The mere possibility of interstellar travel does not imply that every civilization will choose it, yet none of these obstacles make interstellar travel impossible under known law. They make it slow, expensive, risky, and technically demanding. That distinction is important. A nearby civilization with enough time and patience might still launch probes that cross to neighboring stars at a small fraction of the speed of light. Such journeys could take centuries or millennia, but a long-lived technological society or an automated mission might accept those timescales. The galaxy is old enough that very slow projects can still matter if they begin early and persist. This is why the physical limits do not close the question. They set the conditions under which movement between stars could occur. Distance demands time. Speed demands energy. High speed intensifies collisions with dust and exposure to radiation. Biological crews demand life support and social continuity. Deceleration demands further engineering. Communication delays demand autonomy. Every step is difficult. But difficulty over millions of years of civilizational development is not the same as impossibility. The result is a restrained conclusion. Advanced civilizations, if they exist, cannot ignore the laws of physics. They must work within them. Known physics gives no easy road between stars, no rapid passage without cost, and no method for mass-bearing objects to outrun light. It does, however, leave room for slow expansion, long-duration probes, and patient engineering. The next issue is therefore not whether interstellar travel faces limits, because it clearly does. The question is what kinds of missions could realistically operate within those limits and continue moving outward across the galaxy. If interstellar travel occurs under known physics, it likely begins with designs that accept time as a normal cost. The basic challenge is to move a craft across light years while keeping it functional, guided and protected, then to extract useful results at the destination. Several broad mission concepts have been studied in scientific and engineering literature, each with its own advantages and limits. None is proven and none is simple, but each provides a plausible outline of how a civilization might send something between stars without violating physical law. One approach is the uncrewed probe. A probe avoids the biological burdens of life support, food production, medical care, and social continuity. It can be small, robust, and optimized for a narrow set of tasks such as imaging planets, sampling dust, measuring magnetic fields, or listening for signals. A small mass is easier to accelerate, and it requires less shielding and less propellant in many designs. A probe can also be built with redundancy, fault-tolerant computing, and long-lived power sources, though all of these remain challenging over centuries. Even today, human-made probes operate for decades, and some continue far beyond their original design lifetimes. This suggests that with more advanced engineering, long-duration uncrewed missions are at least conceivable. Propulsion options for probes include nuclear systems, beamed power, and sail-based concepts. A nuclear fission system can provide long-lived power and potentially thrust if used in a rocket configuration, though the amount of thrust achievable depends on reactor mass and exhaust speed. Fusion propulsion has long been studied because fusion offers high energy yield and potentially high exhaust velocity, but controlled fusion in compact, reliable form remains difficult. Beamed propulsion is another concept. A powerful laser or microwave beam from the home system could push a light sail attached to a small craft, accelerating it without carrying fuel. This shifts the burden to infrastructure at the departure system, where a civilization might build large energy collectors and beam emitters. The sail itself must endure intense radiation and remain stable in the beam, if successful. This method could send very small probes to nearby stars at significant fractions of the speed of light. Such missions would still face dust and radiation hazards, and they would also face the challenge of deceleration at the destination, since a sail pushed outward by a departure beam does not naturally slow down on arrival. Deceleration can be approached in several ways. A probe might accept a fast flyby, collecting data during a brief passage. It might carry a braking system using stored propellant, though this increases mass. It might use a magnetic sail, a large electromagnetic structure that interacts with the interstellar medium, or the stellar wind of the destination star to slow down. It might also use a light sail in reverse, reflecting photons from the destination star, though the available braking depends on the star's brightness and the sail's properties. None of these methods is easy, but they illustrate that arrival is not automatically the end of the problem. A probe is useful only if it can operate during its encounter, transmit findings back, and in some cases remain in the system long enough for extended study. A more ambitious concept is the generation ship. This is a crude vessel designed for a voyage lasting so long that multiple generations live and die aboard before arrival. It would function as a closed or nearly closed ecosystem, recycling water, air, and nutrients while producing food and maintaining health. Such a system would need stable agriculture, microbial recycling, careful management of waste and toxins, and protection against disease and genetic decline in a confined population. It would also need governance structures that keep the mission coherent across centuries. The craft would require shielding against radiation, either through mass, magnetic systems, or both, and it would likely need some form of artificial gravity to reduce long-term harm from weightlessness. These demands are vast, yet the concept remains within physical law. It is limited mainly by engineering and social endurance. Another crude concept is suspended animation or deep hibernation. If a civilization could place living beings into a state of extremely low metabolism for long periods, the life support burden would shrink. The craft would still need protection, repair capability, and power, but it would not need to support active daily life for centuries. At present, long-term human suspended animation is not established. Some animals can enter states of torpor, and medical science can reduce metabolism for limited periods. But the extension of this to journeys of decades or centuries remains uncertain. It is therefore a concept that cannot be treated as available, though it remains a possible direction for a very advanced biology and medicine. Robotic missions can also take a form that is more than a single probe. A civilization might send a self-replicating system, often called a von Neumann probe. The idea is that a machine arrives in a new system, uses local resources to build copies of itself, and sends those copies onward. Over long times, such a network could spread through many star systems without needing an enormous industrial base at home for each launch. The concept depends on high levels of autonomous manufacturing, mining, refining, and error control. It also depends on a way to avoid runaway replication that consumes resources without purpose. The technical and ethical challenges are substantial, yet as a theoretical mechanism for slow expansion, it is powerful because it converts time into reach. If each probe takes a few centuries to travel and a few centuries to reproduce, a wave of exploration could still cross the galaxy in a time that is short compared with the age of the Milky Way. This is a mathematical observation about multiplication and travel time, not evidence that any civilization uses such machines. A related approach is the seeded infrastructure model. Instead of sending a complete civilization, a society might send automated factories that build habitats, power stations, and communication relays in new systems. These could prepare the way for later arrivals, or they could function as remote outposts operated by machine intelligence. Such systems could also serve purely scientific ends, acting as distributed observatories. The advantage is modularity. Each unit can be small and specialized. The disadvantage is that the whole network still requires enormous reliability, coordination, and protection against failure. All these mission types must address the interstellar environment. Dust impacts remain a limiting factor at high speed. Shielding can involve thick forward mass, layered materials that absorb and spread impact energy, or electromagnetic fields that deflect charged particles. Neutral dust grains, however, are not easily deflected by magnetic fields. This suggests that physical shielding, route selection, and speed limits may remain important even for advanced craft. Radiation protection depends on both shielding and mission duration. Cosmic rays can penetrate deeply, and prolonged exposure can damage electronics and biological tissue. A robotic craft can tolerate some radiation through hardened components and redundancy. A crewed craft must be much more protected. Power sources for long missions also constrain design. Solar power weakens with distance from a star, so beyond the departure region, a craft cannot rely on large solar arrays unless it travels between stars quickly and carries immense collector area. Nuclear power provides long-lived energy, either through fission reactors or through radioisotope systems that produce heat from decay. Future technologies might use fusion, but this remains uncertain. Power matters not only for propulsion, it supports navigation, computing, repair, heat control, and communication. A craft that cannot maintain its systems for centuries cannot complete an interstellar journey. Communication back to the origin system is another barrier. Even if a craft reaches another star, it must transmit across light years. A small probe has limited power and antenna size, making data rates low. A larger transmitter improves communication but increases mass. A probe network could use relays, but that requires additional infrastructure and time. A civilization may decide that a mission's main purpose is local, not to report back in detail, especially if the home society evolves beyond interest or beyond the institutions that launch the mission. This highlights again that interstellar projects are bound to deep time. They may outlive cultures, languages, and priorities. These concepts show that, within known physics, interstellar travel is most plausible as a slow, distributed process carried out by machines, with biological travel reserved for rare cases if at all. A technological civilization does not need to send living beings first. It can send instruments, factories, and autonomous explorers. It can accept journeys of centuries because it measures success over long spans. It can spread gradually, using replication or repeated launches, and it can adapt its designs to the hazards of speed by choosing lower velocities with lower impact risk. In this view, an arriving presence at another star system may not look like a ship of living passengers. It may look like a small probe entering the outer system, adjusting course with quiet thrust, deploying sensors and listening. It may look like a factory descending onto an asteroid to begin mining. It may look like a relay station setting up a long, patient communication beam. Such missions would not need dramatic gestures. They would need persistence, autonomy, and careful energy management. The mechanics of approach therefore become a question of timelines. If probes travel slowly, their arrival depends mainly on how long ago they were launched. The galaxy is ancient, and even slow expansion can cover large distances if it starts early enough. This makes the next inward layer less about engineering possibility and more about chronology. If a civilization arises long before humans, and if it launches a sustained outward program, then some of its probes could already be in transit across the Milky Way. Whether that is likely depends on unknown frequencies of life and on unknown choices of civilization. What can be examined more firmly is the relationship between the age of the galaxy, the speeds that appear physically plausible, and the timescales required for a wave of machines to move from one star to the next. If an advanced civilization arises somewhere in the Milky Way, the possibility that some part of it is already moving through interstellar space depends mostly on age, distance, and patience. The galaxy is far older than human civilization, and far older than Earth's technological phase. Many stars in the Milky Way are billions of years older than the Sun. If even a small fraction of their planets become habitable early, and if even a smaller fraction of those worlds produce durable technological societies, then some civilizations could, in principle, have begun interstellar projects long before Earth formed. The question is not whether this has happened. No observation confirms it. The question is whether the timescales of the galaxy leave room for it under known physics. They do. The Milky Way is more than 13 billion years old, while the Sun is about 4.5 billion years old. This means there is a span of many billions of years in which older planetary systems could have hosted life before Earth existed. Not every old star is a good home for habitable planets. Some early stars form when the galaxy has fewer heavy elements, and some galactic regions are less stable than others. Even so, the galaxy becomes chemically enriched quite early in many places. Rocky planets begin forming long before the Sun. Observations of exoplanets and studies of stellar composition indicate that Earth-sized and larger rocky worlds are not confined to the most recent part of galactic history. This widens the possible age range for habitable environments. Once time is measured in billions of years, the speed required for meaningful expansion changes. A civilization does not need to cross the galaxy in a single leap. It can move in stages from one nearby star to another, taking advantage of local resources and allowing each new system to become a base for later launches. This process has the character of diffusion or of a slow wave. Each step may require centuries or millennia, and each settlement or machine outpost may pause for long intervals before continuing onward. Yet over millions of years, such a wave could advance substantially. Over tens of millions of years, it could spread across a large fraction of the galactic disk. Compared with the age of the Milky Way, these are short spans. A simple numerical picture shows why. The diameter of the Milky Way's stellar disk is on the order of 100,000 light-years. If probes or settlements advance at an average effective speed far below light speed, including time spent travelling and waiting between launches, the total crossing time can still be modest on galactic scales, at 1% of the speed of light. A direct continuous motion across the disk would take roughly 10 million years. At 1/10 of the speed of light, it would take roughly 100 million years. A staged expansion wave, slowed by colonization, pauses and imperfect directionality, would take longer, perhaps much longer, but still not necessarily longer than a small fraction of the galaxy's age. The significance of this is not that such expansion must happen. It is that if any civilization chooses it and persists, there has been enough time for it to have happened many times over. This observation lies behind part of the tension often called the Fermi paradox. If the galaxy is old, if habitable worlds are common, and if some civilizations expand, then why is there no clear evidence of their presence? The paradox is not a proof that extraterrestrial civilizations do not exist. It is a reminder that several unknowns must be large enough to keep the sky quiet. Perhaps life is rare. Perhaps technological civilization is rare. Perhaps long-lived expansionist behavior is rare. Perhaps expansion occurs but leaves subtle traces that have not yet been recognized. Perhaps probes are designed to avoid interference and remain difficult to detect. Each possibility has been discussed, but none is confirmed. The chronology alone, however, remains firm. human radio technology and spaceflight are extremely recent. If another civilization begins an outward program even 1 million years ago, it gains a lead vastly larger than all of recorded human history. If it begins 100 million years ago, the lead becomes almost geological from Earth's perspective. A slow probe travelling for 10,000 years would seem nearly impossible when compared with a human lifetime. Yet, it would be a brief mission when compared with the age of a stable stellar civilization, or an automated system designed to operate over deep time. The barrier is psychological for humans because human institutions are short-lived. Physics imposes difficulty, but time in the galaxy is abundant. A wave of exploration need not be dense to matter. Even a sparse network of probes could spread widely if each system launches only a few successors. The result would not resemble a continuous occupied empire in every star system. It might instead resemble a thin scattering of listening posts, survey machines, and industrial seed units spaced unevenly over millions of stars. Some systems might be bypassed. Some might receive only a passing probe. Some might host long, quiet devices waiting for signs of life or useful resources. This kind of expansion would be much less visible than dramatic stories of universal conquest suggest. It would still count as a civilization being on its way, because parts of its technological activity would remain in motion long after the initial launch era. The choice of speed also affects detectability. A civilization may prefer lower velocities because the energy cost is lower and the dust hazard is less severe. A probe moving at a small fraction of the speed of light can survive more easily than one moving much faster. If the mission goal is not urgent, there is little reason to spend vastly more energy for a faster arrival. In a galaxy billions of years old, patience is efficient. This means an advanced civilization already on its way to many systems might still travel slowly enough to remain faint and difficult to notice until very close by. There may be no brilliant exhaust, no large moving object visible across interstellar distances, and no dramatic alteration of starlight during the long cruise between stars. Old civilizations also need not remain biologically continuous in the human sense. Their outward-moving systems could be robotic, self-maintaining, and culturally separate from their point of origin. A probe launched millions of years ago may still function even if its creators changed beyond recognition or disappeared. In that case, what is on the way is not necessarily a crew or even a living community. It may be a persistent technological lineage, carrying instructions, tools, and autonomous decision systems from star to star. This possibility makes chronology even more important, because machines can in principle tolerate durations that biological societies find difficult to imagine. Still, the argument from age has limits. It assumes that technological civilizations arise often enough and last long enough to begin interstellar projects. It assumes that they choose expansion or large-scale exploration. It assumes that their systems continue functioning over immense intervals. None of these assumptions is supported by direct evidence. The Milky Way's age makes the scenario possible, but possibility is not proof. A galaxy can be old and still mostly silent if the critical steps from life to engineering are rare, or if civilizations commonly turn inward, remain local, or fail before long-term expansion begins. Observations at present do not decide among these options. Astronomy shows a galaxy rich in planets and old enough for many experiments in life to have occurred. It does not show a confirmed interstellar probe, a verified extraterrestrial signal, or an engineered structure in the solar system. The chronological argument therefore remains conditional. If advanced civilizations exist elsewhere in the Milky Way, and if they adopt slow, persistent expansion, then some of their artifacts could already be moving between stars now. They would not need faster-than-light travel, they would need only time, energy, and continuity. This brings the possibility inward toward the solar system. Earth is not hidden in any absolute sense. Its atmosphere has been altered by life for billions of years and by industry for a much shorter time. Its radio emissions have formed a small expanding shell in space. From a distant perspective, the solar system contains a rocky planet with liquid water, oxygen, seasonal change, and now a thin but growing layer of technological activity. If anything is already on its way through the Milky Way, Earth may be just one destination among many, neither central nor exceptional. The scientific difficulty is that no such arrival has been verified. The galaxy allows time for ancient motion to still be underway, but the evidence for any specific mission remains absent. The final step inward is therefore the immediate neighborhood of the Sun, where the question becomes not whether a civilization could have launched something long ago, but whether there is any sign that such a process has reached our own system. The solar system lies in the Milky Way's disk as one ordinary planetary system among many, orbiting the galactic center within the broader middle regions of the galaxy. Its structure is shaped by the Sun's gravity, by the materials left from formation, and by the long history of collisions and orbital evolution. Any discussion of an arrival must narrow to this immediate setting, because this is where evidence would be closest, and where constraints on presence become most concrete. Here, the objects are not distant points of light but bodies that can be visited, mapped, and monitored with instruments. The Sun is a middle-aged star, stable on human timescales, with a steady output that supports liquid water on Earth. Its planetary system includes rocky inner worlds, gas giants, ice giants, and populations of smaller bodies. Between Mars and Jupiter lies the main asteroid belt, a region containing rocky remnants that never formed into a planet, shaped by Jupiter's gravity and by early solar system evolution. Beyond Neptune lies the Kuiper Belt, a collection of icy bodies that includes Pluto and many smaller objects. Farther still is the region from which long-period comets arrive, often described as the Oort cloud, a vast and distant reservoir of icy objects loosely bound to the Sun. These regions matter because they contain the small bodies where a visiting probe might hide or mine, and they also matter because their dynamics reveal whether large artificial disturbances are present. Earth itself has been detectable as a living world for a long time in atmospheric terms. Oxygen has been abundant for hundreds of millions of years, and methane has coexisted with oxygen at varying levels, a combination that can indicate active replenishment. Seasonal changes in carbon dioxide and other gases also reflect global biology. From far away, these features would be subtle but potentially measurable with sufficiently advanced instruments. Over the last century or so, Earth has added signs of technology. Artificial radio transmissions have leaked into space, forming an expanding sphere about 100 light-years in radius. The planet also reflects artificial light at night, though this is extremely faint beyond nearby distances. Industrial activity has raised atmospheric concentrations of certain gases, including carbon dioxide, and has produced other compounds in smaller amounts. Whether any distant observer could detect these changes depends on their instruments and their location. The changes are real, but the signal is weak compared with the brightness of the Sun and the natural variability of planetary atmospheres. If an advanced civilization were arriving, the simplest expectation under known physics is that the first arrivals would be machines rather than biological travelers. A probe could enter the solar system, study it, and perhaps use local resources. It might do so without emitting strong signals and without altering planetary orbits in obvious ways. Therefore, the absence of dramatic disturbance is not, by itself, a strong constraint. More useful constraints come from targeted searches and from the growing completeness of observations within the solar system. Human spacecraft have visited every major planet and many moons, and they have mapped surfaces, atmospheres, and magnetic environments. Mars has been studied extensively by orbiters, landers, and rovers. The Moon has been mapped in detail. Venus has been observed from orbit and by past landers. The outer planets and some of their moons have been visited by flyby missions, and selected moons have been studied more closely. Comets and asteroids have been imaged and sampled by several missions. These explorations have revealed natural geology, natural chemistry, and natural processes in many settings, but they have not found verified artificial structures or artifacts of non-human origin. Astronomical surveys have also improved. Telescopes search for near-Earth objects and track asteroids that pass close to Earth. These programs are designed mainly for planetary defense, but they also increase knowledge of what objects are in the neighborhood and how they move. The distribution of small bodies fits natural models of solar system evolution and long-term gravitational dynamics. No confirmed object has been identified with an orbit or behavior that requires an artificial explanation. There have been occasional discussions of unusual interstellar objects passing through the solar system, but these objects are explained within natural categories such as comets or asteroidal bodies, and the uncertainties involved do not provide evidence of technology. Observations indicate that interstellar visitors in the form of natural debris are possible. They do not indicate that such visitors are probes. Searches for radio signals remain a central part of looking outward, and also of checking the local sky for unusual transmissions. Modern observatories monitor wide frequency ranges and can detect many kinds of natural and artificial radio sources. They regularly encounter human interference, satellites, and the complex radio environment created by Earth. Within this noise, no confirmed extraterrestrial transmission has been established. Claims that require an arriving civilization need strong, repeatable evidence, and such evidence is absent. Within the solar system, a slow-moving probe could potentially remain hidden for a long time if it stays small, cold, and quiet, particularly in the outer regions where sunlight is weak and the background is sparse. This is a genuine uncertainty. The outer solar system is vast, and not every meter has been surveyed. Yet uncertainty is not evidence. The strongest statement supported by present knowledge is that there is no verified sign of an arriving or present advanced alien civilization in the solar system. The data collected by planetary missions, astronomical surveys, and signal searches do not show confirmed artifacts, deliberate transmissions, or engineered structures. This absence can be understood without assuming any particular answer about life elsewhere. If technological civilizations are rare, then the solar system is unlikely to be visited. If they are common but do not travel widely, it may still remain unvisited. If they explore with small probes, those probes may be difficult to detect unless they choose to reveal themselves. If they send probes on long timescales, a probe might still be en route. But being en route is not the same as being here, and the time to arrival cannot be inferred without evidence of launch or trajectory. Earth's own situation offers a quiet perspective on the phrase already on their way. Human beings have only just begun to send small machines beyond the solar system's planets, and even the farthest human-made probes have not yet reached the nearest star. The distances involved mean that being on the way can mean centuries. millennia, or much longer. A hypothetical extraterrestrial probe launched long ago might still be travelling between stars now, passing through the dark spaces where no telescope can easily distinguish it from the background. Such a probe, if it exists, would be difficult to confirm until it entered the solar system or produced a detectable signal. In the immediate environment of the Sun, what is known is limited but solid. The solar system has been explored enough that large, obvious artifacts are unlikely to be present unnoticed on major planetary surfaces. The skies have been watched enough that bright, powerful transmissions would likely have attracted attention. The populations of small bodies and their motions appear natural. Beyond these points lies uncertainty that is normal in science. The outer reaches of the system are wide, and quiet objects are hard to find. It remains possible that something small, passive, or distant could avoid present detection. It remains uncertain whether such an object exists, and there is no confirmed evidence that it does. The innermost conclusion remains calm and bounded. The Milky Way is old enough that advanced civilizations, if they exist, could have launched interstellar missions long ago. Interstellar travel under known physics is difficult but not forbidden. Slow expansion by probes could, in principle, spread across the galaxy within times short compared with galactic age. Yet within the solar system, no verified sign shows that any advanced alien civilization is presently arriving or already present. Observations indicate a natural system with one known technological species still confined near its homeworld, living beneath a sky that is wide, mostly quiet, and still largely unknown. In that quiet, the mind returns to scale. Stars continue their slow orbits around the galaxy. Planets continue their steady paths around stars. Light continues to travel, carrying news of distant events long after they happen. In the space between one world and another, time remains the main distance. What is known is gathered by instruments and careful inference. What remains uncertain is held as uncertainty without adding weight to it. The universe stays vast and patient, and the solar system remains one small system within it, turning in silence and ordinary motion. In the calm boundary between knowledge and the unknown, attention settles on what is immediate. A planet with oceans and cloud bands rotates under sunlight. Its atmosphere shifts with seasons. Its night side glows faintly with scattered human lights. Above it, the moon keeps its steady course. Beyond it, the planets move in their long paths, and the distant stars hold their positions for a human lifetime. The idea of visitors remains a thought shaped by distance and time, while the present evidence remains grounded in what has been observed. The pace slows, and the scene becomes simple. Dust drifts through interplanetary space. Solar wind streams outward, thinning into the dark. Radio waves leave Earth and fade into the background. No clear reply returns. The sky remains open, and the nearest certainty is the gentle persistence of physical law and the slow turning of the earth beneath it. The body of knowledge rests, and the mind can rest with it.